Hello and welcome to lesson 8.4, intersections of lines in 2 space and 3 space. So today we're going to actually examine how interlines interact, and I'm going to use the term interact instead of intersect, in 2 space. The reason why I use the term interact is because sometimes it doesn't actually intersect, and therefore it could be misleading that way. But please realize the textbook does use the word intersect, and that might not mean they actually intersect. So in 2 space, first of all, notice that you could have one solution. This occurs when you have 2 lines that intersect and give you 1 point. You can usually tell this if you have it in scalar form or vector form by looking at the directions and or the normals. You'll notice those 2 values are totally different. There's also the possibility you could have no solutions. This occurs when the 2 lines are actually parallel to each other. Well, in vector form, you'll notice the directions are going to be scalar multiples of each other, but it takes a little bit more investigation in order to determine if they are the same line. However, if you have it in scalar form, you'll notice that these 2 equations are not the same, but the normals are exactly the same. You can also have infinite solutions. This occurs when both lines are the exact same thing. And again, in vector form, you can notice that directions are the same, but again, more investigation may be needed to take place. But in scalar form, you'll actually know the equations are exactly the same thing. So this shows that actually using the scalar form for all of these cases would probably be best. But in 3-dimensional space, you can only use vector or parametric forms. So what are the possibilities? So how lines can interact in 3 space? Well, they could possibly have, again, no solutions. And again, this occurs when the vectors are parallel. You'll notice that here the directions turn out to be scalar multiples of each other, and some more investigation may need to be taken. However, if the direction vectors are still scalar multiples of each other, there is also the possibility you can have infinite solutions. There's also the possibility you can have one solution when the 2 lines actually intersect at a point. Here you'll notice the directions turn out to be actually totally different from each other. There's also the possibility you could have no solutions when you have 2 lines that actually are not parallel but also still do not intersect. These are called skew lines. Skew lines occur when the 2 lines are almost not in the same plane, but one is above the other in different planes. And again, you'll notice that the directions don't turn out to be the same. So what you have to notice here is you have to first identify the directions, and then from the directions you need to do some more investigation before you can actually decide what kind of line you have. So let's take a look at an example. So here we want to determine the point intersection for these 2 lines. Well, to do this, I would actually suggest us change our 2 lines. We're going to call one line 1 and the other one line 2. And we're going to change these into scalar form first. And then we're going to compare them. So for line 1, I'd use a normal of 2, 3. Because again, 2, 3 dotted with 3, negative 2 would be 0. And therefore, my equation would be 2x plus 3y plus c equals 0. I can substitute the value of 18 and negative 2 in. To solve for c. And I get a c value of negative 30. So I get an equation of 2x plus 3y minus 30 equals 0. Do the same kind of idea for line 2. Line 2 would have a normal of 1 and negative 2. Another normal could have been negative 1 and positive 2. I chose not to use that one due to the fact that the leading coefficient was negative. Okay, so x minus 2y plus c equals 0. Substitute my point, negative 5 and negative 4, and for x and y, and solve for c. So c turns out to be 13. Okay, so now we get two equations in terms of x and y. So you can use elimination or substitution to solve for x and y, or you can just try some good old-fashioned guess and check. I suggest avoiding guess and check, as the points might not be the best option to guess and check there. So you can pause your video right now and try some elimination and substitution. So for myself, I'm going to take equation 1. I'm going to leave it as is. I'm going to take equation 2 and I'm going to multiply by negative 2. Then I'm going to add these equations. So here I get a y value of 8. So I can take that value of y equal to 8 and substitute back into equation 2. And I get an x value of 3. So therefore my point of intersection actually turns out to be 3 and 8. Okay, so let's take a look at another situation. So with three-dimensional space, you can see some more options available. First of all, notice that these two directions are non-collinear. So this means they either intersect once or they are skew. No matter which option we have, the best choice to make is to list line 1 and list line 2 in terms of their parametric equations. So line 1 would be listed as x equals 1 plus 3s, y equals 8 minus 2s, and z equals negative 2 plus s. Whereas for line 2, you can write it as x equals 3 plus 4t, y equals negative 1 plus 2t, and z equals 4 plus t. Now, in either case, again, you must see when these lines actually intersect. So values of x, y, and z, that would be the same for both of them. So if the x values are the same, just set them equal to each other, and maybe rearrange the equation. Do the same thing for the y's. And do the same thing for the z values. Now you're set up with 3 equations. With these 3 equations, what you want to do is you want to solve for s and t in 2 of them. If s and t work out for 2 of them, and then you check to see if s and t work out for the third one, then there's a possible value for s or t that would make these lines actually intersect. And that would tell you which option you have. If you have values of s and t that work for 2 of them but not for 3, then there's the possibility that you have skew lines. So I'm going to solve for s and t in equations 2 and 3. So I'll use elimination again. I'll leave equation 2 as is. I'll take equation 3 and multiply by 2. Okay, so I found a value for t. Now I find a value for s. I'm going to substitute it into my third equation. To solve for s. I'm going to leave it as a fraction of 21 over 4. So now we need to verify if that value of s and t actually work. If the values of s and t actually work, then we have a point intersection. And you can then substitute s or t into your original equations and solve. So we're going to check s equals 21 over 4 and t equals negative 3/4 in equation 1. So left side, 3 times that 21 over 4 minus 4 times the negative 3/4, and we want to see if that right side is equal to the value of, what was it, 2. So as you can see, 75 over 4 does not equal 2. Therefore, we have skew lines. No value of s and t work. Okay, some terminology that we need to know. Whenever it talks about consistent set of solutions, what it means is it actually has solutions. So it can have infinite set of solutions, or it can have one solution. If it says it's inconsistent, then it has no solutions. If lines are said to be distinct, they're talking about parallel lines. And if they're saying coincident, they're talking the same line. Just some terminology we need to know. Okay. So to determine the minimum distance between 2 skew lines, the shortest distance actually turns out to be a line that's perpendicular to the directions of these things. So let's say one line has a direction of a vector, let's say we'll call it A, and another line has a direction, we'll call it B. Well, the shortest distance actually turns out to be a line that's perpendicular to both these values. So in other words, we need a vector that's perpendicular. Well, if we find a vector that's perpendicular, let's call it n. N can actually be calculated by taking the cross product of A and B. Now, unfortunately, n might be longer or shorter than the actual distance than the actual physical distance that we need to measure. So the physical distance could be from this point to this point. So what we need are 2 points as well. We need a point P and a point Q on each side of the line, and we need to project it onto this normal. So that means the minimum distance, which we'll give by the letter D, is actually the magnitude of the projection of the vector PQ onto N. Well, if we remember projections, to work out the projection of PQ onto N, all we have to do is take PQ, dot it with the vector N, put it over N dot N, and multiply by the vector N. But now we're looking for the magnitudes of these things. So, again, the magnitude of PQ dot N we can work out. Remember, N dot N is actually just the magnitude of N squared. And we're also multiplying by the magnitude of N that we worked out. Well, you might notice the magnitude of N with magnitude of N in the denominator can cancel out, and therefore a simplified version of this formula, if you want to memorize it, is the magnitude of PQ dot N over the magnitude of N. So now we can actually find out the minimum distance between two skew lines. So let's find out the minimum distance between these two skew lines. No need to prove that these are skew lines, first of all. Okay, so to figure out N, I'm going to write down the numbers 1, 2, 3, 1, 2, 3 off to the side, and 2, negative 1, negative 1, and 2, negative 1, negative 1 off to the side, so that I can work out my normal. My normal is going to be the cross product of 1, 2, 3, and 2, negative 1, negative 1. This is something that'll give me something that's that cross product for both of these. Okay. Pause the video, work out your cross product. Okay, so you should find out this negative 2 minus negative 3 should be 6 minus negative 1 and negative 1 minus 4. So my normal turns out to be 1, 7, and negative 5. The vector PQ is just the physical distance from one point to the next point, which is, you pick one as the starting point and one as the end point. Doesn't matter which one you choose. So I'm going to choose 5, negative 4, negative 2 to start with, and I'm going to subtract 2, 0, 1 from it, so that I can get the vector PQ. So that turns out to be just 3, negative 4, and negative 3. Okay, so now I can work out my minimum distance. I'm going to take PQ, dotted with N, find its magnitude, put this over the magnitude of N. Okay, so 3, negative 4, negative 3. I'm dotting with 1, 7, negative 5. And I'm finding the magnitude of the vector 1, 7, negative 5. So we know how to do these things. Complete these calculations for yourself by pausing this video. Okay, so this works out to be 3 minus 28 plus 20. Oh, sorry, plus 15. Sorry, calculation error on my part. over the square root of 1 squared plus 7 squared plus negative 5 all squared. So this turns out to be a value of positive 10 because I'm taking the absolute value over the square root of 75. If you want to change this into proper format, remember square root of 75 can be written as the square root of 25 and square root of 3. So this is 5 root 3, and this is 10 in the numerator. So this simplifies to 2 over the square root of 3. Or if you want to rationalize it, 2 root 3 over 3. And there we go. And thus concludes this lesson.